Swayam Prabha. Digital India. Educated India.
Okay, so good morning everyone. So last class we were looking at relation between circuit classes and uniform complexity classes. Okay, we saw results like NC1 is uniform NC1 is contained in L and all of NL is contained in NC2, and of course there are these containments that follow somewhat by definition. For example, that NC1 or for any NCI is contained in ACI. Essentially, bounded fan-in circuits can be simulated by unbounded fan-in circuits. But the point is, if we are allowing unbounded fan-in, can we actually shrink the depth, okay, from some d to something smaller than d, okay, and that is exactly what this theorem is characterizing. That if I take a d depth circuit of bounded fan-in, then I can construct another equivalent circuit which has unbounded fan-in but depth d by k for any parameter k. Okay, so k is something that we can choose as long as it is smaller than d. Of course, yeah, if it is bigger than d, then it does not make much sense, because so I can choose d to be smaller and I compress the depth, and of course there is a blow up in size from s to 2s d times 2 to the power 2 to the power k plus 1, but for small enough k this would still be manageable for us. Okay, so we will see what kind of things we can choose. So let us see how the proof goes. So the idea of the proof is quite simple. So okay, so we have the circuit C. Okay, so let me draw a picture first. So we have this circuit C, and if I take, okay, so this is my circuit C. If I take any level, so let us say that C is layered in some sense. Okay, so by layered what we mean is that the gates, so basically every edge of the circuit goes from one level to the another. Okay, so I can partition the gates into layers or levels, and every edge goes from a level I to I plus 1. Now if I look at any level I in this layered circuit, and let us say I look at, okay, maybe let us say I look at I plus C, and I have I over here, I plus K and I over here, then I can somehow represent the output of a gate in I plus K in terms of the gates in level I, okay, up to a depth K. And how will it be? So this is a bounded fan-in circuit. Let us assume, without loss of generality, that the bound is 2. Okay, so we can assume that these are AND or and NOT gates, so over which takes 2 inputs at most. So then basically every gate here would somehow depend on at most 2 to the power k. So this is depth k, so 2 to the power k gates from level I. Okay, and this is basically the idea that we want to exploit. So the point is that it cannot depend on arbitrary many gates from level I, but a small number of gates, and this is what we will exploit to design a smaller circuit. Okay, so okay, I'll give the argument. Okay, so this is just informally I am saying. So informally, basically, if I look at this thing, so every gate here has at most 2 inputs. So if I go down by a level k, it can, I mean the tree can have at most 2 to the power k leaves of depth k. If I take any tree of depth k or any graph of depth k, it can have at most 2 to the power k leaves. That is what I am using. Okay, so we will construct a circuit C prime as follows. So, the first step of the construction is to make sure that we can assume it is layered. Okay. So, firstly make C layered by introducing dummy identity gates. Okay. So, essentially what I am saying is that let us say suppose I have an edge which is going from some layer I to some layer j, okay, and j is let us say greater than I. Then what I will do is that I will introduce some dummy nodes over here, dummy gates over here, which are identity gates. Essentially whatever they take as input, they just send the same thing as output. Okay. So, this is to make it layered. Okay. So, whatever, so there basically I will be adding how many j minus I minus 1 many such dummy nodes for every such edge. Okay. So, initially my size was S and depth was D. So, after layering, the size of the circuit is at most S times T. So, there are, so S you can think of it as the number of edges in the circuit. Okay, so it is a DAG. So, the size of a DAG I can assume it to be the number of edges, and for every edge at worst case I will be adding D many dummy nodes. So, therefore, it is at most S times D. Now, what I will do is that replace levels I to I plus k using a DNF circuit. So, essentially I take a gate over here, okay, and as I said that I will look at all the gates in level I, and I can basically replace it with a DNF circuit. Okay. So, I can think of it as a truth table. So, okay, so how many inputs will it depend on? So, every gate in layer I plus k will depend on at most 2 to the power gates of layer I. Okay. So, essentially you can think of it as a truth table which has 2 to the power k inputs. Okay. And now the size of this truth table will be 2 to the power k. Okay. So, essentially if I am doing a DNF, so I have a OR gate at the top. This OR gate will be an AND of 2 to the power k many. So, this OR gate is basically a combination of 2 to the power k many AND gates, and each AND gate can have at most 2 to the power k variables from this layer. So, essentially, okay, so So, let me write this down. So, the top OR gate will have at most 2 to the power k inputs, and every AND gate below it will depend on at most 2 to the power k inputs. Okay. So, basically you can think of it as I have a truth table over 2 to the power k many variables. So, if I want to do a DNF of this truth table, this is basically the size, okay, and then at the bottom I have literals which are either direct edges or maybe not of something, okay. So, is this clear? So, essentially what I have done is I have reduced okay, now okay, so essentially what am I doing here? So, okay, so maybe I could have done, I should have said this earlier, but I can say it. So, C is divided into, this is not tree exactly, let me write this as a note. C is divided into D by K blocks of K layers each. Okay. So, again pictorially this is what it looks like. So, this was my C. So, I have broken down into the first block of K layers, then again I have K over here and so on, K over here, and the total number of such blocks is D by K, and for each block I am essentially doing this kind of a replacement. Okay. So, each block of K layers I am replacing it with a 3 layered circuit. Okay. So, we will count how many nodes are increasing. So, right now what we have done has reduced C prime from depth D to 3D by K, correct. Now, what about the size? How much does the size increase? Okay. So, after the depth reduction for each gate in layer I plus K, the size of the DNF circuit is at most. So, what does the size of the DNF circuit look like? So, I have so basically I can take any one block and basically I am expanding it to, so I have a OR gate at the top. So, this OR gate depends on 2 to the power k many AND gates, and these AND gates will depend on each AND gate will depend on 2 to the power k many gates from layer I. So, what is the blow up in the size? So, now basically for each gate my size is 2 to the power k many AND gates plus 1 OR gate, right. And of course, I will also be having the NOT gates, but let us just, I am just counting the AND and OR gates, let us say, for the time being. Just write it over here, the AND OR size of the DNF circuit is at most this much. Okay. Now, using De Morgan's, so now I will have some NOT gates, but I can actually shift all the NOT gates to the bottom by using De Morgan's theorem. We can shift all NOT gates to the input level with at most doubling the size. Okay. So, therefore, what we get is, so therefore, we have that depth of C prime is, what is the depth? So, there are D by K layers. So, for every D by K blocks, so for every D by K blocks I have 2 layers now, and then finally I have an additional layer at the bottom of NOT gates. So, this is the depth, and the size is S. So, this I am doing for every gate. So, this is SD. So, when I layered it, the size went up to at most S times D. So, it is SD times 2 to the power k plus 1, and because of applying De Morgan's theorem, this is at most twice. Okay. So, this is a upper bound. So, this proves the theorem. Okay. So, as I said, the idea is actually quite simple. It is just replacing some small depth with a corresponding DNF formula or DNF circuit. Okay, so now as I said last time as well, an immediate corollary is that what we can show, or every function in NCK can be simulated by a circuit by an unbounded Fanon circuit of polynomial size and depth order log to the power kn divided by log n, and the proof is very simple. So, you just take k to be equal to log n, that is it. So, if you take k to be equal to log n, then S times D, which is anyway bounded by a polynomial, times 2 to the power k, which is just n, plus 1 will still be a polynomial, but now the new depth is d by k, which is polylog divided by log n. Okay. So, this is improving upon the observation that NCI is in ACI. Okay. Any questions? I mean, it is reducing by a factor of k, and you can take k to be anything. If you want the size to be polynomial, then you can take k at most log n, because if you take k to be anything bigger than log n, then 2 to the power k will be bigger than polynomial. So, the next thing that we will study is, so we have looked at circuits that are polynomial size but bounded depth. So, now we can just generalize this to any circuit of polynomial size. So, this class P by poly is the class of functions for which there is a polynomial sized circuit family. Okay. So, we do not have any restrictions on the depth, it is just any polynomial size circuit family. Okay. So, now the question is, we have seen relation between these bounded depth circuit classes and uniform classes. What can we say is the relation between, for example, P and P slash poly? Okay. So, that is what we are going to see. So, this is again a sort of an application of okay, I'll come to that. Let me just state the theorem. So, we will prove the following theorem, that let L be a language decided by a Turing machine running in time t of n, then L can be computed by a circuit family of size order t of n square. Okay.